Hello students, I am Professor Isha Medherata from LG Institute of Engineering and Technology. We have started with the 5th chapter, that is last chapter of our syllabus, which is light semiconductor interaction. Until now, we have discussed the topics Einstein's theory, principle and working of laser, semiconductor laser. Then we have discussed what are joint density of states, photovoltaic effect. Based on photovoltaic effect, we have discussed what a solar cell is. And in the previous video, we have discussed what is Drude model, what were the assumptions of this Drude model and its applications. And in today's video, I am going to discuss Fermi's golden rule and EXCITON. I have divided this video into two parts and I'll be starting with Fermi's golden rule first. So let's start with Fermi's golden rule. What exactly is Fermi's golden rule? Let's see what is Fermi's golden rule. In quantum physics, it is used to calculate transition rates, that is the probability of transition per unit time. Let me consider an example of semiconductors and explain you what particularly transitions are. So suppose I consider a semiconductor having a valence band and a conduction band. I can explain you the first type of transition as absorption. So suppose there is an electron which is present in the valence, it will be present in the valence till energy is given to it. After absorbing the energy, electron will move to the conduction band. The other type of transition is emission. If you consider the electron to be in the conduction band, it will come down to the valence band and it will release the energy. So we have two types of transition processes. One is from the lower level to the higher level on absorbing energy. The other one is from higher level to lower level releasing the energy. So this particular formula is going to explain us what will be the probability of transitions per unit time. Transitions, as I said, can be either absorption or emission. Now let's see what exactly is the use of Fermi's golden rule. So the general form of this equation, the Fermi's golden rule, it is applied to atomic transitions as I just explained. Atomic transitions means either absorption or emission, and it is also applicable to nuclear decay and scattering. What do you mean by the term decay? Decay means again releasing of energy, so it is a form of transition only, which can be explained with the help of Fermi's golden rule. Then let us discuss on what factors the transition rate depends. We are going to find out the probability of transitions, right? So let us first see on what factors these transition rates depend. So the first factor is known as the coupling between the initial and the final states of a system. What do you mean by the word coupling? The strength of interaction between the initial and final stages. And secondly, it depends on the number of ways the transition can happen. What do you mean by number of ways? Number of ways can be with the help of light, can be with the help of electric current, or by using any other parameter. So these were the factors on which the transition rate is going to depend. Now, the transition probability, that is what we are going to discuss as a part of Fermi's golden rule. The transition probability is given by the equation lambda IF is equals to 2 pi by h MIF square into ZF, where the term lambda IF is known as the transition probability with respect to unit time. H is the Planck constant. MIF is known as the matrix element for interaction, which I am going to discuss shortly. And ZF is known as the joint density of states. What do you mean by joint density of states? We have discussed in this chapter itself, which will give us the number of transitions per unit time. So probability, the transition probability also depends upon the number of transitions per unit time. This particular equation is known as the equation of Fermi's golden rule. The coupling term is known as a matrix element. So the matrix element is the term MIF. Let's see what exactly a matrix element is. It is an integral term where an interaction is expressed in the form of potential V, which operates on the initial state wave function. So exactly the integral term is what is known as the matrix element, And while defining Fermi's golden rule, what do? Is we take the square of this integral term. Now this integral term will depend upon the potential of the electron. It will also depend upon the wave functions of initial and final stages. So we'll be defining matrix element. So transition probability is proportional to the square of integral of interaction. What is this integral of interaction? It is nothing but the matrix element. And our transition probability lambda IF depends upon the square of this integral of interaction. So I define the matrix element MIF as integration of psi f star V into psi I d nu. What do you mean by the terms psi f star V and psi I? So V here denotes the operator for physical interaction which couples the initial and final stages. I can say that initial stage means the ground state or the lower energy state, and the final stage is nothing but the higher energy state or the excited state. The term psi f star is known as a wave function for final stage, and the term psi I is known as a wave function for initial stages. D nu here indicates the frequency. Because we are considering quantum physics, because we are considering the wave nature of electrons, we will have to consider nu as the frequency. This is the equation with the help of which we define the matrix element, and this particular matrix element square is used to derive the transition probability. A transition can proceed more rapidly if the coupling between initial and final stages is strong. If there is a very good interaction, a very strong interaction between the lower and the higher energy states, the transitions can proceed rapidly, either from lower to higher or from higher to lower. That clearly depends upon how strong the coupling is. And this coupling is nothing but the matrix element, which is based on the wave functions. So we say that transition is actually dependent upon the coupling. Transition probability, which is denoted as lambda, it is also called the decay probability and is related to the mean lifetime tau as lambda is equals to 1 by tau. I can say that transition probability is inversely related to the mean lifetime. So this was about what exactly is Fermi's golden rule. Fermi's golden rule means the equation which is going to give us the probability of transition. And this equation of probability of transition is dependent upon the matrix element, which means the coupling strength between initial and final stages. This was about the first topic for today. Now let us move on to the second topic and discuss exciton. Let's see what an exciton is. The concept of exciton was first proposed by Yakov Frenkel in the year 1931. So he was a physicist who first explained or proposed the concept of an exciton. Let's see what exactly exciton is. It is a bound state of an electron and hole which are attracted to each other by electrostatic Coulombian force. So this is a bound state where an electron and hole, because they being opposite charges, are definitely going to attract. So there will be a Coulombian force of interaction between a negative electron and a positive hole. So this bound state is what exactly an exciton. Let's see how an exciton is formed. When an external energy, say a photon, is absorbed by a semiconductor, what happens? The electron is moving to the conduction band, and this creates an electron-hole pair. Suppose there was one electron in the valence band which is absorbing the energy of photon and it is moving to the conduction band. So hole is created in the valence band. So we say electron-hole pair or EHP is created. Now this electron is now attracted to the localized hole which was left behind by the help of repulsive forces from the large number of electrons surrounding the excited electrons. We, for the explanation purpose, consider only one electron, but there are number of electrons in the conduction band. So just assume one of them. What will the other electrons do? They will repel this electron, and the hole in the valence is already positive charge. So this will actually attract the electron, and there will be a sort of bounded state created between this electron and hole. So what exactly I mean is, this attraction will give us a stabilizing energy balance. Let us see with the help of a diagram. In this diagram, you can see that a photon is emitted, is incident on the electron. The electron is moving to the conduction band. There is a hole left behind in the valence band. And you can just notice that there is a chain sort of surrounding between the electron in conduction and the hole in valence. And this indicates the bounded state of electron and hole, and this bounded state is what is known as an exciton. Now let us discuss the types of excitons. Starting with the first one, we have a Frenkel exciton, named after Yakov Frenkel, who actually explained this. What exactly is Frenkel exciton? Frenkel exciton, let me first explain you this diagram and then we'll see what the definition is. So in this diagram, you can see the arrangement of positive ions. In between them, there is a dotted blue colored circle with an electron, which indicates that the electron is being attracted to the positive ion. You can see the space between the electron and the ion is very less. That means this attraction is very, very strong. So on the basis of this diagram, let me define Frenkel exciton as when there is a strong electron-hole attraction and the electron and hole are tightly bound to each other, such a type of exciton is known as a Frenkel exciton. That means the strength of attraction is very, very high. Let us discuss some properties of Frenkel exciton. So starting with the first one we have, they are tight bound electrons because there is very less space between them. Then we have, they are found in insulators and molecular crystals. Why? Because the strength is very, very high, the ion will not let the electron free, and that is the reason in insulators we do not have conduction. Then we have, the binding energy is very large. It is in the range of 0.1 to 1 electron volt, and that is the reason the electron can't be easily set free. The next property says they are bound to specific atoms, and how do they move? They are being transferred as if they are hopping from one atom to the other. And lastly, we have, they are stable at room temperatures. Room temperature, if you say, is around 300 Kelvin. So the electrons do not have very high energy, and that is the reason the hopping is very, very less. And we say that these excitons, because of the strong attraction, are stable at room temperature. So these were some of the properties of Frenkel exciton. Now let us move and discuss the second type of exciton, which is known as the WANNIER-MOTT exciton. So again, with the help of a diagram, let me tell you what a WANNIER-MOTT exciton is. So in this diagram, you can see the positive ion arrangement, and in between them there is a huge circle which has a hole and an electron present. What does this indicate? That there is a huge gap between the hole and electron, or I can say the attraction between this hole and electron is comparatively less if we consider with respect to Frenkel exciton. So now I define the WANNIER-MOTT exciton as when the electron-hole separation is much larger than the lattice constant, the exciton is called the WANNIER-MOTT exciton. So if the separation is larger, the attraction will also be less, and such a type of exciton is the WANNIER-MOTT exciton. Let us now discuss some properties of WANNIER-MOTT exciton. The first property says they are free excitons. Because of less attraction, the electron gaining some energy can be free for conduction, and that is the reason they are known as free excitons. Then we have, they are found in semiconductors. That is the reason why semiconductors conduct when temperature increases. If you increase temperature, if there is a change in temperature, even at room temperatures, what happens? These excitons become free because the electrons are released from the bounded state and they are available for conduction. And so we say, whenever the electron is available for conduction, the exciton is lost because now there is no bounded state. Next property is their binding energy is weak. You can say 1/100th of Frenkel exciton. It is around 0.01 electron volt. And because of this low binding energy, electrons can be easily free. Next property is they are delocalized states which can move freely throughout the crystal because of less attraction, of course. And the last property is they are stable at cryogenic temperatures. What do you mean by the word cryogenic? Cryogenic temperatures means very, very low temperatures. Even if you talk about room temperatures, the excitons, WANNIER-MOTT excitons won't be present. So they are stable if you consider very low temperatures only. So this was about properties of WANNIER-MOTT exciton. So in today's video, we have discussed what is Fermi's golden rule, How do you find the probability of transitions with the help of matrix element that defines the coupling. Then we have discussed what an exciton is and the two types of exciton along with its properties. Hope you have understood all the topics I discussed very well. Today, with this topic, I am completing my chapter number 5 and also the syllabus of physics. Hope you have enjoyed learning with me. Thank you again.